Okay, everyone, let's get started. Welcome back to Theory of Computation, lecture number 6. So we have been looking at a number of different models of computation. And last lecture actually was an important one for us because we shifted gears from our restricted models, finite automata, push-down automata, and their associated generative models, regular expressions, and context-free grammars, to Turing machines, which are going to be the model that which is the model that we're going to be sticking with for the rest of the semester, because that's going to be our model, as we're going to argue today, for a general purpose computer. So in a sense, everything we've been doing up till now or up until that point, has been kind of a warm-up, but it's been, nevertheless, has gotten a chance for us to introduce some important concepts that are used in practice, and also will serve as good examples for us moving forward. And also just to get our, get kind of, in a sense, on the same page. What we're going to be doing today is looking at the Turing machine model in a little bit more depth. One can define Turing machines in all sorts of different ways, but it's going to turn out not to matter, because all of those different ways are going to be equivalent to one another. And so we are going to stick with the very simplest version, the one we've already defined, namely this the simple one-tape Turing machine. But we're going to basically justify that by looking at some of these other models and proving equivalence. So we'll look at multi-tape Turing machines, we'll look at non-deterministic Turing machines, and we'll look at another model which is slightly different, but is still based on Turing machines, called an enumerator. And we'll show that those all, in the end, give you the same class of languages, and so in that sense, they're all equivalent to one another. And that's going to serve as a kind of a motivator, kind of to, in a sense, recapitulate some of the history of the subject, and going to lead to our discussion of what's called the Church-Turing thesis. So we will, I'll get to that in due course. And we'll also talk about some notation for languages, and notations for Turing machines and for encoding objects to feed into Turing machines as input, but we'll get to that shortly as well. So let's move on. Then we will next go into a little review of what we did for Turing machines, and just want to make sure we're all together on that. The very important concept for us this term. So the Turing machine model looks like there's going to be this finite control. There's a tape with a head that can read and write on the tape, can move in both directions. The tape is infinite to one side, and so on, as I mentioned last time. The output of the Turing machine is either going to be a halt, accepting or rejecting, or loop, that the machine may run forever. With 3 possible outcomes for any particular input, the machine may accept that input by entering Q accept, may halt and reject by entering Q reject, and it might reject by looping, which means it just never gets to the accept state, or it never gets to any halting state. It just goes forever. But we still consider that to be rejecting the input, just it's rejecting by looping. Okay, and as we defined last time, a language is Turing recognizable, or as we typically write, T recognizable, if it's the language of some Turing machine, the collection of accepted strings from that Turing machine. Again, just as before, a machine may accept 0 strings, 1 string, many strings, but it always has one language, the collection of all accepted strings. Now, if you have a decider, which is a machine that never loops, which always halts on every input, then we say its language is a decidable language. So we'll say a language is Turing decidable or simply decidable if it's the language of some decider, which is a Turing machine that always halts on all inputs. So we have those two distinct notions, Turing recognizable languages and Turing decidable languages. Now, as we're going to argue this lecture, Turing machines are going to be our model of a general purpose computer. So that's the way we're going to think of computers, as Turing machines. Why Turing machines? Why didn't we pick something else? Well, the fact is it doesn't matter. And that's going to be the point of this lecture. All reasonable models of general purpose computation, unrestricted computation in the sense of not limited memory, have been shown, all the models that we've ever encountered have all been shown to be equivalent to one another. And so you're free to pick anyone you like. And so for this course, we're going to pick Turing machines because they're very simple to argue about mathematically. And also they have a sort of some element of familiarity in that, they feel like, they're more familiar than some of the other models that have been proposed that are out there, such as rewriting systems, lambda calculus, and so on. Turing machines feel like a primitive kind of computer, and in that sense, they have a certain familiarity. Okay, so let's start talking about variations on the Turing machine model, and we're going to argue that it doesn't make any difference. And then this is going to be kind of a precursor to a discussion of a bit of the history of the subject that we're going to get to in the second half of the lecture. So a multi-tape Turing machine is a Turing machine, as you might imagine, that has more than one, well, it has one or possibly more tapes. So a single tape Turing machine would be a special version of a multi-tape Turing machine. That's okay. But you might have more than one tape, as I've shown in this diagram. Now, how do we actually use a multi-tape Turing machine? Well, you present and we're going to see these coming up for convenience. Sometimes it's nice to be working with multiple tapes. So we're going to see these later on in the semester a couple of times as well. But for now, we're setting the model up so that the input is going to be presented on a special input tape. So that's where the input appears, and it's going to be followed by blanks, just as we had before. And now we have these potentially other tapes, possibly other tapes, which we call them work tapes, where the machine can write other stuff as it wishes, and those tapes are going to be initially blank. So just all blanks on them. All of the tapes are going to be read and write. So you can write on the input tape. Obviously, you can read from the input tape, and you can read and write on the other tapes as well. So what we want to first establish that by having these additional tapes, you don't get additional power for the machine in the sense that you're not going to have, you won't have additional languages that you can recognize by virtue of having these additional tapes. I mean, you could imagine that having more tapes will allow you to do more things. For example, if you have a push-down automaton with 2 stacks, you can do more languages than you can with 1 stack. So it's conceivable that by having more tapes, you can do more languages than you could with one tape. But in fact, that's not the case. One tape is as good as having many tapes. And we're going to prove that, we're going to quickly sketch through the proof of that fact. So the theorem is that a Turing machine, a language is Turing recognizable. And when we say Turing recognizable, for now we mean just with 1 tape. That's the way we've defined it. So a language is Turing recognizable if and only if some multi-tape Turing machine recognizes that language. Okay, so really another way of saying that is if you have a language that you can do with a single tape, you can do it with a multi-tape and vice versa. So one direction of that is immediate, because a single tape Turing machine is already a multi-tape Turing machine that just happens to have 1 tape. So the forward direction of that is there's nothing to say. That's just immediately true. But if we want to prove the reverse, then we're going to have to do some work. And the work is going to be showing how do you convert a multi-tape Turing machine to a single-tape Turing machine. So if we have something that's recognized by a multi-tape Turing machine, it's still Turing recognizable. And what that means is that you can do it with a single-tape Turing machine. So we have to show how to do the conversion. And I'll kind of, I'll show you that, I think in a convincing way, but without getting into too much detail. So here is an image of a multi-tape Turing machine during the course of its input. So we've already started it off. Initially it starts off with the other tapes, the work tapes being all blank, but now it's processed for a while. And the head on the input tape has moved off from its starting position at the left end. It's somewhere in the middle. It's written stuff on the other tapes. And what we want to do is show how to represent that same information on a single tape Turing machine in a way which allows the single tape Turing machine to carry out the steps of the multi-tape Turing machine, but using only its single tape by virtue of some kind of a data structure which allows for the simulation to go forward. Okay? So how is the single tape Turing machine going to be carrying out the same effect of having these multiple tapes on the multi-tape Turing machine? So here's a picture of the single tape Turing machine. It just has one tape. By the way, I should mention that all of the tapes are infinite to the right in the multi-tape Turing machine, just as we had for the single tape Turing machine. And now with this single tape Turing machine, it's going to represent the information that was that's present on these multiple tapes, but using only the single tape. And the way I'm choosing to do that is going to be particularly simple. I'm going to just divide up. So here I'm saying it in words. It's going to simulate M by storing the contents of the multi-tape on the single tape in separate blocks. So I'm basically going to divide up the single tape Turing machine's tape into separate regions, where each one of those regions is going to have the information that was on one of the tapes in the multi-tape machine. So for example, here is on the first tape, it's got AABBA. Well, that's going to appear here in that first block on the single tape Turing machine. Okay? Sort of seeing it float down to suggest that it's coming from this multi-tape Turing machine. But that's really been developed by the simulation that the single tape Turing machine has. Obviously, the single tape Turing machine doesn't have any direct access to the multi-tape machine, but it's going to be simulating it. So this is how we're showing the data is being stored on the single tape machine's tape. So in the second block, it's going to have the contents of the second tape of the Turing multi-tape machine. And the final region of the single tapes, the final block, so-called, of the single tapes tape is going to have, single tape machine's tape, is going to have the rest of the contents of the last tape of M. And then it's going to be followed by the same infinitely many blanks that each of these tapes are going to have following the portion that they may have written during the course of their computation. Okay? So that's what the single tape Turing machine's tape is going to look like during the course of its computation. It's going to have the information represented in these blocks, capturing all of the information that the multi-tape Turing machine has in a perhaps somewhat less convenient way, because the multi-tape Turing machine, we didn't really make this explicit, and in part because it doesn't really matter. We didn't say exactly how the multi-tape Turing machine operates. What I have in mind is that the multi-tape Turing machine can read and move all of its heads, from all of its heads, in one step. So in a single step of the multi-tape machine, it can obtain the information that's underneath each of its heads, feed that into its transition function, and then together with the state of the multi-tape machine, decide how to change each of those locations, and then how to move each one of those heads. So it's kind of operating on all of the tapes in parallel. Okay, so now how does the actual steps of the simulation of the single tape, by the single tape machine, how does it go? So first of all, besides storing the contents of each of the tapes in S's single tape, there's some additional information that it needs to record. Namely, M has a head for each one of its tapes, but S has just a single head. And each of M's heads could be in some different location. In this case, as I've shown it, on the first tape, its head is in location 3. On the second tape, it's in location 2. On the third tape, it's in location, on the last tape, it's in location 1. So where were we? We were simulating the multi-tape Turing machine with the single tape Turing machine, and we had to keep track of where the heads are. And so we're going to do that by writing the locations on those blocks. Okay, so we're going to have a special dot, as I've shown here, to represent the location of the head in that very first block. So the head's on the B, I'm going to dot the B, and I'm going to do the same thing for the locations of the others heads. And how am I getting that effect? Well, we've seen something like that before, where we just expand the tape alphabet of S to allow for these dotted symbols as well as the irregular symbols. We also have expanded it to include the delimiter markers that separate the blocks from one another, which I'm writing as a pound sign. So we can just get that effect simply by expanding the tape alphabet of S. Okay, a few more details of S that are just worth looking at, just to make sure we're kind of all understanding what's happening. So for every time M takes one step, S has actually a lot of work to do, because one step of M, it can move all of those, read and move all of those heads all at one shot. S has to scan the entire tape to see what's underneath those, in effect, virtual heads, which are the locations of the dotted symbols. It has to see what's underneath each one of those heads to see how to update the transition, update its state to the next state. And then it has to scan again to change the location, change the contents of those tape locations, and also to move the head left or right by moving effectively now moving the dot left or right. So that's pretty straightforward. There's one complication that can occur, however, which is that what happens if on one of the tapes, let's say, M starts writing more content, then you have room in that block to store that information. So if M moves, it has 1, 0, 1. Suppose M, after a few steps, moves its head into the originally blank portion of the tape and writes another symbol there. We have to put that symbol somewhere because we have to record all that information, and the block is full. So what do we do? Well, in that case, S goes to a little interrupt routine and shifts all of the symbols to the right one place to open up a location here where it can write a new symbol for continuing the simulation. So with that in mind, S can maintain the current contents of each of M's tapes. And let me just note that here. Shift to add room is needed. And that's all that happens in this during the course of the simulation. Okay? And of course, if S, as it's simulating M, observes that M comes to an accept or reject state, S should do the same. Okay, so that's our description of how the simulation of the single tape simulation of the multi-tape machine works. Right? Okay, let's turn to non-deterministic machines. Now, if you remember, for finite, and I hope you do, for finite automata, we had equivalence between non-deterministic and deterministic. finite automata. For push-down automata, we did not have the equivalence. We didn't prove that, but we just stated it as a fact. There are certain languages that you can do with non-deterministic push-down automata, which is the model we typically hold as our standard. So that some things you can do with non-deterministic push-down automata that you cannot do with deterministic push-down automata. You really need the non-determinism. They're not equivalent. For Turing machines, we're going to get the equivalence back. So we'll show that anything you can do with a non-deterministic Turing machine in terms of language recognition, you can also do with a deterministic Turing machine. So remember, we kind of mentioned this briefly last time. The non-deterministic Turing machine looks exactly like a deterministic Turing machine, except for the transition function where we have this power set, which allows for multiple different outcomes at a given step instead of just a single outcome that you would have in a deterministic machine. So we represent that with this power set here, applied to the possibilities that the machine would have as the next step. Okay, so now we're going to prove a very similar theorem that A is Turing recognizable by an ordinary one-tape Turing machine. That kind of goes without saying, so that's how we defined it. A is Turing recognizable if and only if some non-deterministic Turing machine recognizes that language. Okay. Again, remember, we're using non-determinism in the way we always do, namely that a non-deterministic machine accepts if there is some branch or some thread of its computation ends up at an accept. Other branches might go forever or might reject part of the way through, but acceptance always overrules them if any branch accepts. That's how non-determinism works for us. Okay, so now, the forward direction of this is, again, just like before, immediate, because a deterministic Turing machine is a special kind of non-deterministic Turing machine which never branches non-deterministically on any of its steps. So that forward direction is immediate. The backwards definition is where we're going to have to do some work, converting our non-deterministic Turing machine to a deterministic Turing machine, and we'll do so as follows. We'll take a non-deterministic Turing machine. Here's our picture, and we're going to now imagine its computation in terms of a tree. So here is the non-deterministic computation tree for n on some input w. So n for non-deterministic. Here is the tree. Somewhere down here it might end up accepting. And as I mentioned, that is going to be defining the overall computation to be accepting if there is some place here that's accepting. And the only way it can be non-accepting computation if there is no accept that occurs anywhere. And somehow, if you're going to convert this non-deterministic machine to a deterministic machine, the deterministic machine is going to have to get that same effect, though it only has it doesn't have the non-determinism. So how does it manage that? Well, it's really going to be carrying out the simulation, kind of as you would imagine doing it yourself if you were told you had to simulate a non-deterministic Turing machine, which is you're going to search that tree of possibilities, looking to see if you find and accept. If you do, then you accept. If you don't, well, maybe you'll go forever, or maybe you'll manage to search the entire tree, and then you will say, no, I accept. No, I reject. Okay, so let's just see again what the data structure of that deterministic machine's tape is going to look like. So the way this simulation is going to carry out, and you could program this in a host of different ways. And in fact, the textbook has a somewhat different simulation, but I think this one here lends itself a little bit better, and maybe it's a little simpler for description in this setting. But there's lots of different ways of improving these things. So M is going to simulate N, kind of a little bit similar to the previous simulation. It's going to break the tape up into blocks, and it's going to now store in each block a different thread at a particular point in time of N's computation. So you imagine where M is going to be simulating N, sort of doing the same parallelism, but getting the effect of the parallelism, not through the non-determinism, but by maintaining copies of each of the threads on its tape and then updating them accordingly. So the idea is, I think, not too complicated. So let's just see some of the details here. So here populating those blocks with the contents of N's tape on different threads at a sort of, maybe that corresponds to N's tape, after the 5th step of N, on each of those threads. You have these 3 possibilities, let's say, written down as 3 different blocks. Now, remember, in the case of the multi-tape simulation, we needed to record some extra information. In particular, we had to record the location of the heads by using those dotted symbols. We're going to do that again, because each one of these threads might have their head in some different location. But we're going to have to do more. But let's do one thing at a time. We're going to store the head location. Here they are all written down as dotted symbols. But now there's something that goes further, because in a multi-tape case, there was one global state that the multi-tape machine was in, of course, at any given time. It's just that one has one finite control, it's in one state. But in the case of the non-deterministic machine that we're simulating now, each thread can be in a different state. So whereas before we could keep track of the multi-tape machine's state inside the single tape machine's finite control, now there could be many, many different states to keep track of. So you won't be able to store that in a finite control anymore, because there could be some huge number of threads active at any given stage. And some of them can be in one state, others can be in different state, and how do you keep track of all that? So we're going to have to use the tape. We're going to actually write down which state a given thread is in on that block. And we'll do that, I'll show it like this. So writing down the state of each thread in the block by writing down symbols which correspond to those states. So we're actually, in a sense, writing the states down right on top of the block using symbols that correspond to those states. So again, we're getting that effect by increasing the tape alphabet of M to include symbols that correspond to each of its states. And we're going to write those symbols down. So here's the symbol for state Q8 that says, well, that very first thread of N's computation is in state Q8. It's in this 3rd position of its tape, on its tape. The head is on the 3rd position there. And the tape contents is AABA. That's how we represent that thread of the computation, including the state. Okay? Now, so M is going to carry out that step by step, maintaining that information on its tape. There again, similar to before, there might be some special situations arising. So for example, N is not non-deterministic. So a thread might fork into 2 threads. What do we do then? Well, sort of the reasonable thing. If there's a forking thread, M then copies that block, makes 2 copies of the block to correspond to the 2, or however many copies you need, to correspond to the possibilities that that thread is branching into. So you want to represent them all on different blocks of M's tape. All right? And then if M ever finds out that on one of the threads it's entering the accept state, it can just shut down the whole computation at that point and say accept. Okay, so perhaps a little elaborate, but I think conceptually, hopefully, not too bad. Now, let's move on then to talk about somewhat of a different looking, well, sort of a different model in a way, which has some historical significance and sometimes is a helpful way to look at Turing recognizability. And incidentally, you have a homework problem on this model called an enumerator or a Turing enumerator. So here, it's going to operate somewhat differently. First of all, we're going to enhance the Turing machine model. It's going to now have just a single tape, but it's going to also have a printer. Okay, so we're now adding in this new device into the Turing machine called a printer. The Turing machine has tape as before, except we never provide any input to the machine. The tape always starts out fully blank. It's only used for reading and writing. Only used for like keeping for work. It's not the way you present the input. So how do you talk about the language of the machine? Well, the way you work this machine is you take this enumerator. It's a deterministic Turing machine with a printer, as I mentioned. You start it off in blank tape, and it runs and runs and runs, and periodically it can print a string under some sort of program control, which I'm not going to spell out for you. But you can imagine you might have to define the machine in such a way that when it goes into a certain print state, so we're not going to set that all up, then whatever string is in a certain region of the tape, maybe from the start point up into the head location, that gets printed out on the printer. And then it can print out other strings in due course. And so periodically, you think of this printer as printing out a string under the control of the Turing machine enumerator. And so these print strings, these strings that could print out W1, W2, they appear. And the machine might possibly go forever and print infinitely many strings, or it might go forever and only print finitely many strings, or it might stop after a while by entering a halting state. Accepting or rejecting is irrelevant, but it enters a halting state, and then the strings that it's printed out, the finitely many strings it printed out, are just, that's the output of the machine. Now, the language of the machine is the collection of all strings that it ever prints out. So we're defining language in a somewhat different way here. It's not the strings that it accepts, it's the strings that it prints. So we think of this machine almost a little bit analogous to like the regular expression or the grammar, in the sense that it's a generative model. It produces the language rather than accepts the strings in the language. So it's not really a recognizer, it's a generator. And the language of the machine, as I'm writing over here, for an enumerator here, we say that its language is a collection of strings that it prints. Okay? Now we will show that a language is Turing recognizable in the previous sense, recognized by some ordinary Turing machine, if and only if it's the language of some enumerator. And actually, this is kind of a little bit of an interesting proof. You have to do some work. It's an if and only if. Now, neither direction is immediate. You're going to have to do some work in both directions. One direction is a little harder than the other. We'll start off with the easier direction. Let's say we have an enumerator. Hopefully you got this concept of this Turing machine, which periodically prints strings when you've started it off on the empty tape. So now what I'm going to construct for you is the Turing machine recognizer, defined from the enumerator. So this recognizer is going to be simulating the enumerator. So it's basically the recognizer is going to launch the enumerator. It's going to start off simulating it. Now, if you want, if it's convenient, we could use several tapes. We can use one tape to simulate the recognizer, and you have other tapes available for convenience if you want, because we already showed multi-tape and single tape are equivalent. So if you want to think of M as having multiple tapes, it's not going to really be that relevant to my conversation. But you're going to simulate E starting on the blank input as you're supposed to. And then you're going to see whenever E prints an X, you're going to see if X is the same as the input to the recognizer. You get the idea? So we have a recognizer. It has an input string, maybe like 1101. And I want to accept that string if it's one of the strings that the enumerator E prints out. because that's what the recognizer do. It's supposed to accept all the strings that the enumerator prints out. So I got this 1101. What do? I fire up that enumerator, I get it going, and I start watching the strings it prints out, comparing them with my input string, 1101. If I ever see it print out a 1101, great. I know I can accept because I know it's in the enumerator's language. But if I compare and compare and compare, I never see the enumerator ever printing out my input string 1101. Well, I just keep simulating E. If E halts, well, then I can hold and reject if I've never seen that string coming out as an output. If E doesn't halt, well, I'm just not going to halt either. I'm going to go forever, but then I'm going to be rejecting my input by looping. Okay, so that's the proof of converting in this backward direction, which is the easier direction. Now let's look at the forward direction, which has a certain wrinkle in it that we're going to have to get to. So now we're going to be building our enumerator to simulate our recognizer. Okay, and the way we'll do that is the enumerator has to print out all of the strings that the recognizer would ever accept. So you're going to do the obvious thing. You're going to take the enumerator is going to start simulating the recognizer M on all possible strings, sort of, one by one, doing them in parallel, taking turns. You never know, we maybe we didn't make this so explicit, but you don't have, you can sort of time share among several different possibilities. You run, it's sort of like having different blocks for the machine. You're going to run. The enumerator is going to run the recognizer on, well, let's just say it does it sequentially. It runs it on the empty string, it runs it on the string 0, it runs it on the string 1, runs it on the string 0, 0. These are all the possible strings in Sigma star. You run on all of them, and whenever the enumerator, this is wrong. Whenever whenever M accepts, then print, I can't write very well, print W. WI, oops. Okay, so I'm gonna just say it in words. You're going to simulate M on each WI. Whenever you notice M accepting WI, you just print out WI. Because you want to print out all of the strings that M accepts. Now, there is a problem here. So hopefully you're not confused by this typo. Doing it sequentially, like I just described, doesn't quite work. So let me just back that up here. Doing it sequentially doesn't quite work because M might get stuck looping on one of the WIs. Like, maybe when I feed 0 into M, M goes forever because M is rejecting 0 by looping. But maybe it also accepts this next string in the list, the string 1. I'll never get to 1 by just feeding the strings into M one by one like this. What I really have to do is run all of the strings in M in parallel. And the way I'm going to indicate that is I'm going to simulate M on W1 to WI for I steps for each possible I. So I'm going to run M on more and more strings for more and more steps. Okay, and every time I notice that M accepts something, I print it out. So I will fix this in the version of the file that I publish on the website. So if you're still not getting it, you can look there. But just to make things even worse, I have a check-in, which is going to be about this one little point here. So I got a question, where do we get the WI strings? The WI strings are simply the list of all strings in sigma star. So we can, under program control, we can make M go through every possible string. Like if you had an odometer, you're going to first get to the empty string, then you go to the string 0, then the string 1. You can write a program which is going to do that. And the Turing machine can similarly write code to do that, to get to each possible string one by one. And then that's what the enumerator is doing. It's obtaining each of those strings and then feeding them into M, seeing what M does. What I'm trying to get at here is that it's not good to feed them in, run M to completion on each one before going to the next one. You really kind of have to do them all in parallel to avoid the problem of getting stuck on one string that M is looping on. All right, so this is relevant to your homework, in fact. If I convert M to an enumerator in this way, does that enumerator always print the strings out in string order? String order is this order here. Having them, having the shorter strings coming up before the longer strings, and within strings of a certain length, just doing them in lexicographic order. Hopefully you follow that, but since these are not correctnesses, that doesn't matter for us. Let me launch that poll. I'll see how confused, how random the answer is here. So a fair amount of confusion. If you're confused, obviously you're in good company there. Okay, about to shut this down. 5 seconds to go. Okay, ending it now. All right. So the correct answer, as the majority of you did get, is in fact that the order is not going to be respected here when E prints things out. It might print out some things later in the order before earlier things in the order. What's going to control how when E is going to print it out? It really is if M accepts some strings more quickly in fewer steps, then E might end up printing out that string earlier in the list than some other string that might be a shorter string. Because the order in which E is going to now identify that M is accepting those strings depends upon the speed with which M is actually doing the accepting. So you have to, this is relevant to one of your homeworks, because if what you're going to be asked to show is that if you start with a decidable language instead of a recognizable language, then you can make an enumerator which always prints out things in order, in the string order. Okay, and vice versa. So if you have a string which an enumerator which prints things out in string order, then the language is decidable. Okay, so you need to think about that. One direction is a fairly simple modification of what I just showed. The other direction is a little bit more work. Anyway, why don't we take our little coffee break here. Okay, so that's an interesting question. So one question is, if there's, because sigma has an infinite, sigma star is infinite. If I understand this question correctly, which says, it's an infinite number of strings here, how does the machine even get started? Because it has to go through and enumerate all of it. No, it's not first writing down all of those strings. Because you can't write down, and you can't do this infinite step of writing down all the strings. What I had in mind is you're going to take each string in turn. First, you're going to take the first string on the list of sigma star, run M on that string, and then the next string in sigma star, run it on that string, and so on, string after string. And so you're never going to have infinitely many strings to deal with. It's just going to be more and more strings as you're going along. And the question I was trying to get at is whether you're going to run each one to completion before you get to the next one, or you're going to kind of try to do them all in parallel, which is what you need to do to prove this there. Won't there be infinitely many WI? Yes, so there are a similar question, infinitely many WI. There are infinitely many WI, but it's just an infinite loop that we're in. One by one, you're taking care of more and more WI as you're going. Let's see here. Yes, so another question is, are we running it all on all the strings in parallel? Yes, we are running things running all of the strings in parallel, but it's running them in parallel, but these are, we're not defining a parallel Turing machine. It's running them in parallel using time sharing. It runs a little bit in this block, runs a little bit in that block, and in another block, and sort of shifts around and sort of does a few steps of each, and that's how it's getting the effect of the parallelism. Okay. Question is, would the enumerator essentially have a print tape and a work tape? Yeah, you could think of it as having a print tape, however you want to formalize it. It doesn't matter. I mean, I'm being a little whimsical with attaching it to a picture of a real printer, but yeah, it's just, you think conceptually you can have it a print tape, however you like to think about it, it's fine. How can we directly say that without knowing the program of the printer? The printer is just, we don't have to get into the structure of the printer. The printer is just something where you say print a string and a string comes out. That's all we know about the printer, and that's all we need to know. So there's no program for the printer. Sorry if I not understanding your question, but the question literally says, how can we say that without knowing the program of the printer? So if the machine is decidable, why does it have to print all strings in order? For example, if one string is shorter, can it be decided later? Well, yeah. If the reason why we want, so the question is, if the machine is decidable, why does it have to print all strings in order? Because that's what I'm asking you to do in the problem. That's what if you read the problem, I think it's number 5 on the P set. That's what I'm asking you to do. That's why you have to print it in order. Otherwise, you wouldn't have to worry about printing in order. It's just because I'm asking you to. Okay, so I think we're out of time. Let us move back into our material. Okay, second half, Church-Turing thesis. So Church, this is going back into the bit of the history of the subject back to the 1930s. Back then, people were interested in formulating the notion of what do we mean by algorithm. They didn't even call it algorithm. And they call it, some people call it procedure, some people call it effective procedure, some people called it effective calculation. But people had in their minds, mathematicians have been dealing for centuries, thousands of years, with procedures for doing things. That's a very natural thing. And mathematical logicians, in particular Church and Turing, Turing is somebody you surely obviously have heard of, Church maybe not. Church was Turing's thesis advisor, in fact. And they both were coming out of the mathematical logic field of mathematics, and trying to use mathematical logic to formalize this intuitive notion of what we had for centuries about what a procedure is, what is an algorithm, and back in those days, they came up with different ways of formalizing it. So here we had this notion of algorithm, which is kind of an intuitive concept. Turing proposed Turing machine as a way of capturing that in a formal way, in a mathematically precise way. Other people came up with other ways of doing it. And back then, it wasn't obvious that all of those different formulations would end up giving you equivalent concepts, equivalent notions. And And in fact, they proved in fairly elaborate detail that the different methods that people came up with, it was the lambda calculus, there was rewriting systems, there were several methods that were proposed for formalizing this notion, and they all turned out to be equivalent to one another. In today, that seems kind of obvious, even though I went to some effort to prove that, just to give you a feeling for how those things go. If you have programs, if you have Pascal and Java, say, and thinking about what you can do mathematically in those, I'm not talking about their ability to interface with, Windows and so on, but just the mathematical capabilities, the capability of doing mathematical calculations or functions with a Pascal program or a Java program. It would be absurd to think there's some program that you can write in Java that you can't write in Pascal. Or Python. And the reason is we know you can compile Python into Java and you can compile Java back into Python. And that tells you that the two systems of two programming languages are equivalent in power. That wasn't obvious from the get-go to these folks. So they observed that all of the different efforts that they came at formalizing algorithm all were equivalent to one another. That was a kind of a breakthrough moment when they realized that not all of the ways that they've come up with, and once they got the idea, they realized all reasonable ways of doing it are always going to be equivalent. And so that suggested that they've really captured this notion of algorithm by any one of those methods, say a Turing machine. And that's what they took. You can't prove that because algorithms are an intuitive notion. But the fact that we're able to capture that in a formal way, that's what we call today the Church-Turing thesis. Okay, that is, so any of these methods capture the notion of algorithm as we described. And that has had a big impact on mathematics. So now I just want to, just give me 1 second here. All right, here's a check-in on this one. So Alan Turing, so here are some facts which may or may not be true about Alan Turing. Now you get to pick all of the ones that apply based on your knowledge. Obviously, this is not something, this is more for fun, but or historical interest. But here is, let's launch that poll, see how much you know about Mr. Turing. Check all that apply. Okay, almost done. Please, let's wrap it up. I think that's everybody. Okay, 2 seconds, please get credit for doing this. And polling, in fact, it's kind of interesting here. You all do know that he was a code breaker. He was in fact, was part of a team, I think led the team, which broke the German code during World War II. The Turing test is a famous thing for how do you characterize when you have an intelligent machine. So he definitely worked in AI. He worked in biology as well. He has a paper that less well known to computer scientists, but if you look him up on Wikipedia, where I get all my information, he actually, and I knew this anyway, he has a very famous paper, an influential paper, on how, for example, spots arise on leopards and stripes on tigers and so on. He gave a kind of mathematical model for that, which actually proves, is does capture things in an accurate way, as was shown subsequent to that. Was imprisoned for being gay. In fact, as far as I know from his history, he was not imprisoned for being gay. He was convicted of being gay and was given a choice to go to prison or to take chemicals to cure him from being gay. And he opted not to go to prison and take the chemicals. Sadly, he committed suicide 2 years after that. So he was treated very treated very badly by the British society and British government, despite having the great work that he had done. You might think that he has been honored by appearing on a British banknote. That's also not true. But the good news is he's not currently on a British banknote, but he's going to be on a British banknote starting next year. So that is, so that's, you know, along with Winston Churchill and a number of other notable Brits, he's going to be on the 50-pound banknote. Okay, so let us continue. So as I mentioned, the Church-Turing thesis is important for mathematics, and it has to do with these Hilbert problems. I don't know how many of you have encountered that. David Hilbert was widely considered to be perhaps the greatest mathematician of his day. You know, every 4 years, mathematicians get together for an international congress called the International Congress of Mathematicians. It was, you know, even that's been going on for over 100 years, and he was invited to the 1900 meeting to give a talk about anything he wanted. And what he decided to do during that presentation is present 23 problems that would be a challenge for mathematicians for the coming century. You know, we're running a little short on time, so I'm not going to go into them. Some of these we'll talk about later. But the 10th problem here is about algorithms. The 10th problem on Hilbert's list, often called Hilbert's 10th problem, is a problem about algorithms. And it says, give an algorithm for solving what are called Diophantine equations. He didn't call it an algorithm. He called it some you know, finite procedure or something like that. But, you know, what are Diophantine equations? I'm glad you asked. Diophantine equations, what are they? Well, they're very simple. They're just polynomial equations, like, you know, does this polynomial equal some constant, for example? But where you're looking for the solutions, you know, the polynomials are variables, you're looking for the solutions, but you're only allowing the solutions to be integers. So here's an example. So here, I give you this polynomial. Here I'm setting it equal to 7, and I want to solve that equation. So it has these 3 variables, x, y, and z. So you have to find a solution there, but I'm only going to allow you to have plug-in integers. And in fact, there is a solution in integers, 1, 2, and -2. If you plug it in, you'll see it works. All right. Now, the general problem that Hilbert was addressing is, suppose I give you a polynomial. Let's say it's set to 0, so we're looking for roots of the polynomial, but just some polynomial equation. You can always put it in this form. And I want to know, does it have a solution in integers? And what I'm looking for is a procedure which will tell me yes or no. I want to know, give an algorithm to answer that question for a given polynomial, or using the language of this course, defining this in terms of a language, decide this language. Give a Turing machine which will decide yes or no for any given polynomial. Yes, there is a solution in integers. No, there is no solution in integers. Okay? And that is that was what Hilbert asked in his 10th problem, give an algorithm. Now, as we know now, it took 70 years to get the answer that that there is no such algorithm. It's an undecidable problem. And we'll talk about that a little bit later in the term. But there is, D is not a decidable language. Now, there was no hope of coming up with that answer in 1900 or even in 1910, because we didn't have a formal idea of what an algorithm is. That had to wait until the Church-Turing thesis told us that algorithms really are Turing machines, that there is a formal way of saying what an algorithm is. And once you had that notion, then you could prove that there is no Turing machine. But before that, you had only this vague notion, intuitive notion of what an algorithm is. And so there was no hope of ever answering that, because in fact, the answer is there is no such algorithm. Okay? Now, I'll give this as a little exercise to you. We're a little bit running short on time, but this language D is in fact a recognizable language. So I would suggest you think about that offline. But basically, you can try plugging in different values for these variables. And if you ever find that it evaluates to 0, then you can accept, but otherwise you just have to keep going and looking. So showing recognizability is very simple, but decidability is false. Okay, now let's talk a little bit about encodings for Turing machines. We're going to be working encodings and Turing machines. So we're now going to be working with Turing machines going forward. The input to those Turing machines might be polynomials, might be strings. They might be other things too. We might want to feed automata into the Turing machines, so the Turing machine can answer questions about the automata. Well, don't forget, Turing machines take as their input just strings. So we have to think about how we're going to represent something more complicated like an automaton as a string. And I'm not going to get into the details of that. You could spell it out in detail, but I think that's not too interesting to get into that. We're just going to develop a notation that says, if you have some object, O, it could be a polynomial, it could be an automaton, it could be a graph, it could be whatever you're working with, a table. I'm going to write that O in these brackets to mean an encoding of that object into a string. And then you can feed the string into the Turing machine. Okay, so that's how we're going to be thinking of presenting Turing machines with more complicated objects and strings as input, because we're just going to represent them as strings using some ways in which I'm sure you're all familiar. I mean, that's how you deal with representing stuff when you're, write your programs anyway. But just to make it formal, and that's the way we're going to write it down in these brackets. And if you have a list of several objects that you want to present together to a Turing machine, we'll just write them together within brackets like this. Now, for writing Turing machines down, going forward, we're going to be using high-level English descriptions. We're not going to be worrying about managing like the stuff we've been doing up till now. I'm not going to ask you to do it. We're not going to do that anymore, and I'm not going to ask you to do it. Managing where stuff goes on the tapes and all that stuff, that's too low level. Because really, now that we have the Church-Turing thesis, we're really interested in talking about algorithms. We're not that interested in talking about Turing machines per se. We're interested in algorithms and what the power of computation is. So we're going to only be talking about Turing machines now in a higher level way. And only when we need to prove something about capabilities, we're going to come back to Turing machines and we're going to be proving things, about their limitations and so on. So our notation for writing Turing machines is going to be, we're basically going to put the Turing machine inside these quotation marks, and we're going to know that we could, if in principle, write out the Turing machine in a precise way in terms of states and transition function and so on, but we'll never actually go ahead and do that lengthy exercise. So quick check-in here. So one of the features, well, okay, let me not give this away. So if X and Y are strings, I want to now have a way of presenting two strings as a single string as input to my machine, because I always think of my machine as getting a single input. So would you suggest one way of combining two strings into one, which would be a good encoding, is just to concatenate those two strings together? Would that be the way you would do it? Is that a good way to do it, or not such a good way to do it? So let's see here. I can get to that next. And think of what you would want to have happen in a good encoding. Okay? Ready, set, sold. Share results. Yeah, I think most of you got the idea that this is not a good way of combining two strings into one, because the problem is it's kind of ambiguous in a sense, that you could, if you combine two strings this way, what's important in an encoding is that the machine, when it gets the encoding, it can decode them back into the original objects. And if you're just going to be sticking the two strings together, you don't know where one string ends and the next string begins. And so it's not going to be a good way of combining things. You should find a little bit more clever way of either introducing another symbol or doing something a little bit more sophisticated, which would allow you to be able to do the decoding as well as the encoding in a unique way. Okay, so getting back to that notation for a Turing machine. So here is a machine we've already seen once before for A to the K, B to the K, C to the K. I would write it now more simply than managing all of the tapes that we had the first time around, which we did last lecture. I would just say I would give it an input W, check if W is of the right form with the things in the right order, reject if it's not, count the number of A's, B's, and C's in W, accept if all the counts are equal, and reject if not. We're not going to be, that's going to be good enough to be writing things at that higher level when you're going to be writing your algorithm descriptions. You just have to make sure that whatever you're doing, you can implement. You know, you can't make, you don't want to be doing tests which are impossible or doing infinitely much work in one stage. That's not good. But as long as it's clear that what you're doing is doing only a finite amount of work in every stage and it's something that you could really implement, you can write it at in a high level. Okay. I wanted to spend a few minutes talking about problem set 2, but we're a little bit running out of time here. In particular, there was this problem number 5, where you show that a language is Turing recognizable if and only if there's a decidable D, where C is Turing recognizable, where D is now a collection of pairs. We got some questions about the notation, which I've hopefully answered now. So C is a set of X's such that there exists a string you can pair it with so that the string XY is in D. Let me try to give you a picture of that. So I'm going to think of D as a collection of pairs of strings, and it might be helpful to think of D kind of, you know, on the axes here. So if we have a pair of strings XY, which I have not yet packaged into a single string, I'm thinking of them as a pair of 2 objects at this moment. Think of D as, so, you know, just the X part is just below here on the X-axis. D, you might want to think, just conceptually, want to think of it as a collection of pairs. So it's like a subset of all of these pairs. And C is all of the X's that correspond to any pair in here. Sometimes we call that the projection, because it's all the things that are below, or the shadow. If you had a light sitting up here, it's all the things that are kind of underneath a D. So I've written C here kind of a little thicker, if you can see that. So that's the C language. And there's 2 directions here. One is a lot easier than the other. If I give you a decidable D, and I want to test whether something's in C, so I give you an X. I want to know, is X in C? Well, you now have to test, is there some Y that I can pair with X where the pair is in D? So, you know, you can start looking for that Y. If you ever find one, you know that X is in C. There are infinitely many Y's to look for, but don't forget, you know, you're only looking for a recognizer for C. So, you know, on the rejecting side, you're allowed to go forever. So I'm kind of giving you a way to think about the easy direction. The hard direction, you need to think about how are you going to come up with that decidable D. If I give you C, you have to find a decidable D. And now you're bringing something down lower. You're starting with a recognizable language and a decidable language, which is going to sort of be counterpart to that. In a sense, is a simpler language. And the way it becomes simpler is that Y is going to help you determine whether X is in C. And I guess the thing that I'll leave you with is, and maybe we can talk about this a little bit more on Tuesday. I'll try to leave it a little bit more time. If you want to test if something's in C, X is in C, but I don't want to let you go forever anymore because I want to be a decidable language. And I'm going to use Y to help you. What information would help you guarantee you get the right answer for X being in C? but that you would have to be sure you're getting the right answer. So it's, Y could just be the answer, but then, you don't know that that's, you have to be convinced that you have the right answer. Y just saying what it is, I mean, Y could say that X is in D even when it's not true. X is in C even when it's not true. But so what information would allow you to check that X is in C? What would be helpful information to check that X is in C where you would avoid ever having to go forever? A little bit too rushed here for that to be helpful. Anyway, let's just conclude what we've done. Just brief summary here. And I don't want to keep you over time. So I'll just leave this up on the board. I will see if there's any. So what the lecture is over, and you can take off as you wish. I will stick around for a couple of minutes. I have another meeting soon, but I'll try to answer some chats. All right. People are commenting about this movie about Turing, The Imitation Game. If you haven't seen that, I recommend it. Is it a good idea to make Y to be equal to the repeated loop string? I'm not sure about that. Thank you everybody for sending your kind notes. Church-Turing thesis, the question is it in the book? Yes, it's in the book. Kind of similar to what I've already said, but yes. Okay, this is a good question here. The Church-Turing thesis, somebody asked me, is it proved in the book? There's nothing to prove. The Church-Turing thesis is an equivalence between the intuitive and the formal. You can't prove something like that. You can just it's really, in a sense, a hypothesis that the only thing you'll ever be able to compute is something that you can do with a Turing machine. That has something to do with the nature of the physical world, and I don't really think that's what people had in mind. It's that, the kinds of things that we normally think of being able to do with a procedure mathematically is exactly the kinds of things that you can do with a Turing machine. So somebody's pointing out, trying to be helpful here. Maybe these folks are asking about the equivalence of various different computation models being proved in the book, not the Church-Turing thesis itself. Well, that's the things that we proved in lecture are also proved in the book, about the equivalence of single tape machines, multi-tape machines, non-deterministic machines. Those are all proved in the book. There's lots of models out there, so we could spend a lot of time proving equivalences. And there are books that do spend a lot of time proving equivalences, but I think, I think what we've given is probably enough. So that's a good question. If you give an algorithm, okay, if you give an algorithm, you don't need to give the actual machine going forward, unless you're explicitly asked to. But yes, you don't have to give the states and transitions anymore. Okay, so it's a little after 4. I think we're gonna move on to my next meeting. So I thank you for being here, and I will see you on Tuesday.